Okay. All the best for the last session. Thanks for staying back. After this, we have the happy hour, so we'll wind this up and we'll head out.
Okay. Yeah, thanks for staying. I know it's a little over time. My name is Wes Madrigal. I'm co-founder and CEO of a company called Kurve. We're a recent spin out of a lab down the road, SRI International, formerly Stanford Research Institute. Pre-Kurve, I was a ML engineer for about 11 years, really before there was kind of ML ops. And for the couple of years just before forming Kurve, I was an ML ops consultant. And that was really what led to a lot of these solutions to these problems that we're going to talk about. And all of it really connects back with Iceberg. But we're going to read all this text. Just kidding. The main piece here to focus on is a large portion of data discovery still involves understanding relationship context between tables. So if you want to do any analysis on a particular problem or answer a particular question, a lot of times it's going to require understanding the relationship context between the tables, not just, the column data types and the column names. In Iceberg, the relational metadata that are out of the box are pretty limited. So really what we're trying to infer for an ERD, an entity relationship diagram, is primary keys, foreign keys, date keys. So many tables might have numerous dates, but the one you might be most interested in for analytical purposes is one particular one, probably the date at which the event was emitted or the physical real world transaction was created. And then cardinality, right? One to many, many to many, one to one, et cetera. So all these metadata are required for robust analytics and ML and classical ML, but they're not available in modern data lakes, specifically Iceberg, out of the box. So just one more piece in sort of why these matter. I come from kind of the classical ML space where you start with a question, you look in your data lake, you have to find the subset of data sets that are relevant to that model, that question. Once you find the data sets, you need to understand the relations, which is joins. Finally, maybe a few weeks later, you get to do some joining, filtering, aggregation, and what's classically called sort of feature engineering. And then ultimately you can go and, XGBoost, fit, whatever model you want. But all this pre-work, data discovery and feature engineering, is really where all of the work is at. And even in the Gen AI boom, this is still required. So this was my previous life as a consultant. I would interface with a new lake, sometimes literally every couple of weeks, me and my team, and we would spend weeks to months understanding the data lake, the intricacies of the relational metadata context, just so we could build our first model. And ultimately, this became really problematic when we would onboard multiple at one time, right? So we ended up starting to think about, how can we infer these relational metadata automatically and cut down our onboarding time to new data lakes from weeks to months to hours and days. And that was really the genesis of Kurve. So how you do this is, how we're doing it is you start sequentially by first finding the primary keys on all the tables. And so this involves things like, of course, data type checks, the ordinals, the semantics, uniqueness, things like that. Once you've got all the primary keys, you can start looking at what foreign key candidates potentially point to those primary keys across different tables. And to do that, that's really the essence of it. You run through and you essentially loop through all of the candidates and do type checks, semantic checks, text embeddings, a bunch of data profiling, and finally, maybe some joins. Ultimately, that's going to refine your candidates and you're going to get a metadata relationship graph. So structurally, it looks something like this. This would be your Iceberg tables. And first, primary keys, then candidate generation, filtering, and finally, you've got the relationships between two tables. This is just an example, two data frames where you might have 3 columns in each, and there's presumably a relationship between these two data frames. But the way we go through and operate this, we enumerate all the potential candidates first. Then we would do something like a type check that cuts the 9 candidates down to 3. Then we would do something like a BERT text embedding similarity that cuts the 3 down to a ranked 3. And then we find that these 2 columns are most closely connected. Finally, we might run a join, and then that join actually prunes out the rest, and there's only one foreign key between these 2 tables. For building these ERDs, we've chosen graphs because graphs are a very versatile data structure. This is actually a real data lake graph that we built where each node is a table and each edge is a relationship between tables. Different subgraphs within an enterprise graph could be schemas. They could be literally entire product databases. But they work really well for these problems. So this would be an example Iceberg schema, just a few tables. And this is what we're looking at today in the Snowflake or Unity catalog, just a list of your tables. So in Kurve, you just add the Iceberg REST URI, create a graph, and out pops a relationship metadata graph. All those algorithms that in the details we went through before, that just automatically happens. And you get this rich relational metadata context of all your tables. So you get what you have in Iceberg, but you have this additional layer of all the relationships automatically inferred out just by the click of a button. We can also push these edges back to the Iceberg catalog, so you can actually push back the relationships as a separate table within a schema, which houses all that relational context, which you can then feed to any of your favorite LLM context engines or whatever you want to do to optimize text to SQL. There's just another view of a schema that's actually an open schema. It's called the AdventureWorks dataset. Microsoft released it. But on the left, we turned it into Iceberg tables. On the right was the Kurve output of the relational richness that you get. So you get all this relational hierarchy structure that's in your data that you can't see in just an enumerated list of tables. And that's actually what you need to do any robust analysis. Here is just a slightly different schema, and you can kind of see these are the S3 Iceberg tables. And of course, you got the columns and the data types, but what you really want is the total context of your data for any analytics. One thing this really allows is, most problems are oriented around a particular database dimension. So a dimension would be, a person, a customer, a store, whatever real world thing that your data models. And most problems center around a particular one of those dimensions. So the problem is, how do you rapidly create different shaped data structures for ML models and analytics? And by leveraging Kurve's relational context, you can quickly see what the local neighborhoods relative to any given dimension are. On that top one, we were looking at the transaction processing benchmark data set, the customer dimension. It's 65 million records. So to build an ML model or do an analysis relative to that, you would want a 65 million row by M, where M is the number of columns, data set, so that you don't have duplicate customers. Below would be the store dimension. So the store only has 12 records, but you might want to bring in, the count of customers at that store, which is essentially aggregating that 65 million into 12 records. So the idea is, how can you quickly shapeshift your entire data lake around arbitrary dimensions quickly, which is where 60 to 80% of the data work is, and rapidly shove those ML and analytics ready rich data sets with all the relational context into inference engines, right? So this is what we're really trying to streamline. Again, just kind of to put a picture to that process, right? The process is really, you have all this data, it's just listed out in your Iceberg data lake. You want to see the relationships and rapidly transform it into different shaped matrices and data frames for training, inference, etc. So we've streamlined that whole process. Yep, so this would be kind of what it looks like to build a compute graph. Once you've actually got the relationship graph on your Iceberg tables, you can simply pick, say, a parent node, which would be the dimension at which you want to orient your data. And then you would pick something like a compute period if it's time series data. So, a year, 2 years, 3 years. And then you would pick for most relational ML problems something that you're targeting, right? Something you're trying to forecast in the future, and that would be another node. Could be, transaction, a product, something like that. And that ultimately builds a rich multi-table data set, and we push that back to your Iceberg catalog as an Iceberg table. So kind of the full end-to-end process there of discovering relationships, leveraging those relationships, merging a ton of tables together, and then pushing them back to the catalog, all right at the top of Iceberg. I personally think this should be an additional spec in Iceberg, just to have foreign keys. I don't know why it's not there yet, but been chatting with people. I think it fit in nicely. That's an Iceberg manifest file. Yeah, and then the benefits. I mean, we're doing some of these. We're not doing all of them, but obviously, tribal knowledge is cataloged there in the relationship context. We can integrate with automated feature engineering to loop over all of your data lake, given the relational context, and merge it together, doing aggregations along the way with the cardinality. And I have a friend, he wrote this paper with it, where the plots from, and they were able to achieve significantly better text to SQL performance when the agent was grounded in SQL relational facts, because it actually knows how to join. There's no hallucinations between, say, 1,500 tables and how to join them. So when you ground your text to SQL agent in the relational context metadata facts, it does a lot better. And it gets better and better as the schema complexity increases. So as the schema complexity is high and the metadata are not present, the LLM performs terribly. But when you empower it with some relational context metadata, it gets pretty good even on high complexity schema and high complexity questions. So here's our current integration. It's pretty standard integration map, but we source from different compute layers and we push to different storage layers. So we kind of interop in between different compute engines. We treat them as an abstract concept. You can plug in any compute engine you want. And then we source from, any of the big storage layers, but for this conference, we're really talking about Iceberg. And yeah, it's late, so I wanted to breeze through that. Thanks for staying. We're looking for partners, and we'll be hosting a meetup with Databricks in about 3 weeks. We're at our offices, so thank you.
I have one question.
Yeah.
So when you talk about the candidate tables, is it what provided by customer, or how you scope the candidate list of the candidate tables?
We just loop over the entire data lake. So we crawl the whole lake.
I see.
Yeah.
So you don't need the customer's input for
No,
candidate.
I can come into a fresh lake, and in an hour, I know everything.
Does it have to be Iceberg spec?
No, it can be raw S3 files, Parquet, it can be Snowflake tables, it can be Databricks tables, it can be Athena tables, doesn't matter.
You infer the metadata as part of the process?
So first we go in and we kind of just do a metadata mirroring. So we pull out what's readily available, right? Data types, column names, etc. Then we loop over everything, generate primary key candidates, do a filtration process, select those primary keys. Then we generate the foreign key candidates, the edges, which there could be millions in some cases. And then we condense that down even further through a process. Finally, out pops your actual relationships, right? And then we build this metadata graph with it. So
when you loop, is it loop data or meta, like a catalog metadata, catalog information?
Oh, yeah. So we do both. We use metadata and then we also do data profiling. So we might grab samples of an array of values from the column and see what it looks like, right? So that we can tell, hey, this one's string, but this one's an address, this one's a name. We need to know that those don't connect. And then we do things like semantics, of course, on both the data level and the header level to figure out, conceptually, what is this word about? Is it about people or is it about, events, right? And does that events actually connect with this events from this other company's data that you acquired in a merger and acquisition, right?
So what happens when we do schema evaluation? Should we do
Yeah. So we just rerun.
the
It's
whole
like,
data set, is it?
so we would do deltas, right? So you already have your metadata graph, and it would just be a slight delta on that. But we are early. We're currently running just a few customers, but and the range is about, I would say, 1,000 to a few thousand tables in their data lakes. Two are on, a couple are on Databricks, and so we haven't hit a limit yet in terms of what we can do. Some of our benchmark data sets are in the tens of thousands of tables, so millions and millions of candidates and petabyte scale, and we're able to do that. So,
Well, would you add statistics as well?
so currently we don't add any statistics in terms of usage and anything like that. We're simply trying to build, fill a gap that currently exists, which is the totality of your data context is not there. Even in an Iceberg lake, you're missing all the relational context, right? And that's necessary for analyzing it. So we're just adding that layer. We're integrating with some compute, but we're not really competing with data quality monitors, systems like that, Monte Carlo, things like that. We don't do anything.
Thank you.
It's actually pretty practically useful when you have a huge number of.
Oh, this was the bane of my existence as a consultant. I mean, I'm not kidding. I would onboard 3 or 4 data lakes in a month. And me and my team were just trying to learn as quickly as we could. So just streamline it, completely automated. So
The use cases, like you mentioned, started with machine learning, all this, but this is the main use case for now.
yeah, I mean, different companies are looking at it from different things. We're talking to a Fortune 100 right now, and they're looking at it just for data integration. Right? They buy data sets every week, and they just need to map them. How does it integrate with your wider data set? They buy a company, and then they have to map that data set. So,
Do you map it to Neo4j or?
no, it's actually SQL-like behind the scenes. And the nodes are no. It's just metadata representation. So,
Very interesting, and the solving real problems. We're interested to know if there's any industry element of it, when you are looking at probabilities of